In the last video, we saw how to solve force puzzles in 1 and 2 dimensions. In this video, we will discuss an important force, friction, as well as puzzles with more complicated geometries. To this day, friction remains a poorly understood force. If you wanted to win the Nobel Prize in Physics, one way to do it would be to fundamentally improve our understanding of friction. To keep it simple, though, we can say friction is a resistive force. It occurs when the grooves in rough surfaces interlock and chemical interactions occur between the atoms in each. We'll use this animation to visualize friction. The object is standing still. A small push doesn't move it. The push needs to be of a certain strength before the object starts moving. Consider this question. You have to push a 150 kilogram wooden object along a rough wooden floor. What force must you apply before it starts moving? And B, what acceleration will the object have after it starts moving? To answer this question, we first need to examine the types of friction. The first is called static friction, and it applies when something is standing still. Static friction is a very unusual force. Suppose the character initially pushes the object with 100 newtons of force and sees that it doesn't move. The free body diagram would look like this. The familiar weight force, normal force, and applied force are all here, and we can deduce that there must be a static friction preventing any acceleration or indeed motion. We can even use Newton's second law to figure out that the static friction must have a size of 100 newtons in this case to exactly balance out the applied force. Now, our character pushes with 200 newtons of force. It still doesn't budge. The free body diagram now looks like this, and we can calculate that the static friction must now also be 200 newtons. The size of the static friction changed. Static friction is capable of growing larger or smaller based on the size of other forces to prevent motion. If you push with 100 newtons, static friction increases to 100 newtons. If you push with 200 newtons, it increases to 200 newtons. In fact, here's the equation for static friction. The variability of static friction is given by that lesser than or equal sign. Basically, this equation says that static friction can take any value up to a certain threshold, and that threshold value is given on the right side. The n on the right side is our familiar normal force, but there's a newcomer here. That's the Greek letter mu, and it is called the coefficient of static friction. The coefficient of static friction is a number with no units. It tells you how slippery two surfaces are. It depends on the materials that are being used. Trying to push a wooden object on a wooden floor is harder than trying to push the same object on ice. Every pair of materials has a unique coefficient of static friction, and several pairs are listed in a table in your textbook. The coefficient of static friction for wood on ice happens to be 0.14. Wood on rubber is 0.9, and wood on wood, the materials used in this question, 0.5. These values are measured or empirical. They are not easily derived. And while it takes a few steps, we can find what the threshold value of static friction might be. We'll start with the force balance in y. Normal force points up, weight points down, the acceleration is 0. We can solve for the weight force. It is 1,471.5 newtons. Substituting that into the force balance, we find that the normal force is also 1,471.5 newtons. Next, let's do the force balance in the x direction. We can find the maximum allowed value of static friction by multiplying the coefficient of static friction by the normal force. That's 0.5 times 1471.5, or 735.75 newtons. That is the maximum allowable value of static friction. If our character exerts a force higher than that, then the object will start moving. What about part B? If you overcome static friction and start moving the object by pushing with 735.75 newtons of force, what acceleration will it have? Well, because the object is moving, static friction no longer applies. Instead, we have to account for the second major type of friction, kinetic friction. Unlike static friction, which only applies to stationary objects, kinetic friction only applies to sliding objects, that is, objects that are moving but which don't have wheels. The equation for kinetic friction is like this. It is very similar to static friction, but while static friction can have variable values, kinetic friction has a fixed value that depends on the normal force and a new parameter called mu sub k. As you probably guessed, mu sub k is the coefficient of kinetic friction, and it's only used for sliding objects. For any pair of materials, the value of mu sub k is different and virtually always less than the value for mu sub s. As we saw before, for wood on wood, mu sub s was 0.5. Mu sub k is only 0.3. The difference arises because it is virtually always harder to start something moving than it is to keep something moving. Hence the coefficient of static friction being larger than the coefficient for kinetic friction. To return to part B. In this situation, the forces in the y direction are identical to the ones for part A. The applied force is also the same as in part A. The only difference is there is now a force of kinetic friction. The value of kinetic friction is easy to find. It is 441.45 newtons. We take this value and put it into the force balance. Simplifying, we get the acceleration of the object, 1.962 I hat meters per second squared. In this question, we calculated the minimum force required to overcome static friction and start the object moving. We also solved for the acceleration of the object when it starts moving, and kinetic friction, which is weaker than static friction, takes over. At this point, we've seen all the main forces we can expect from this course. But so far, all the forces have been pointed in either the x or y directions. What happens if a force is pointed in some other direction? Consider this situation. You pull a 20 kilogram object along the floor using a rope. You apply a force of 100 newtons. The rope is angled at 30 degrees above the horizontal. The coefficient of kinetic friction is 0.1. What is the acceleration of the object? We'll start in the usual way, by drawing a picture and then drawing the free body diagram. We will next set our origin and axes. We immediately notice that the tension in the rope is not pointed along either axis. Instead, we see it is oriented 30 degrees above the horizontal, as was said in the question, and we know its size is 100 newtons. In other words, we have been given the size and angle of orientation of a force vector. This is polar notation. But this whole time, we've been doing our calculations in Cartesian, x and y. Before we can use the tension force, we need to convert it into Cartesian. And that's exactly what we do. The angle is expressed in the standard form, with positive x being 0 degrees and counterclockwise being the positive direction. So we apply our familiar formulas for turning a polar vector into a Cartesian one. The horizontal component is given by t cos theta, that's t cos 30 degrees, and the vertical component by t sine 30 degrees. we will use these components rather than the original vector in our calculations from here on out. Let's write out the force balance in the y direction. There are now two forces pointed up, the normal force and the vertical component of tension, T sine 30. And there's one force pointed down, weight. We can substitute these into Newton's second law. We first need to find the weight. It works out to 196.2 newtons. The object is not moving in the vertical direction, up or down, so the acceleration in y is 0. Substituting in the weight and the value of tension, the only unknown is the normal force. It works out to 146.2 newtons. Now we turn to the x direction. There are two forces in the x direction, the horizontal component of tension and kinetic friction. First, we solve for friction. 0.1 times the normal force yields 14.62 newtons. Then we substitute in the other knowns. And finally we solve for the acceleration, 3.6 I hat meters per second squared. Note that we had to solve the y direction even though there's no motion in that direction. That's because we needed the value of the normal force to find the friction force. Note also that for the first time, the value of the normal force did not equal the value of the weight force. That's because the vertical component of tension is partly responsible for supporting the weight of the block, so the normal force becomes smaller. You might have noticed this yourself. If you lift an object slightly, it suddenly feels a lot easier to move along the floor. That's because that slight lift decreases the normal force, and since the friction force depends on the normal force, it decreases the friction force as well. This is the process for solving puzzles where certain forces don't neatly point along x or y. Such forces will be given in polar, and we have to convert them into Cartesian in order to solve them. We can expand the concepts we've seen to more complex cases. Consider this situation. Two tugboats pull a 1,000 kilogram object using ropes. The object accelerates at 0.1 meters per second squared eastwards. One tugboat pulls with a force of 500 newtons oriented at an angle of 10 degrees north of east. The force of friction is 600 newtons. What is the strength and direction of the second tugboat's pull? We start by drawing a picture. Logically, if the overall pull is eastwards and one pull is north of east, the other pull must be south of east. Next, we draw a free body diagram and set origin and axes. There are two tensions, both at oblique angles. Kinetic friction is always opposite the direction of motion, so it points west. Before we can proceed, we must break the tensions into their respective components. The first is easy to do. We just use T1 cos 10 degrees for x and T1 sine 10 degrees for y. But the size and angle of the second tension are both unknown. We will call them T2 cos theta in x and T2 sine theta in y. Next, we set up the force balance in the y direction. The total force is T1 sine 10 degrees minus T2 sine theta. We can substitute the known information. There's no motion in the y direction, so the acceleration is 0. Simplifying, we get T2 sine theta equals negative 86.82 j hat newtons. Note that there are two unknowns here. We cannot solve further without information in x. In the x direction, the force balance contains T1 cos 10 degrees plus T2 cos theta minus kinetic friction. Applying Newton's second law, all of that is equal to mass times acceleration. Plugging in the known information and simplifying, we get T2 cos theta equals 207.6 I hat newtons. Now, back in the y direction, we got T2 sine theta equals negative 86.82 j hat newtons. If we were to divide the expression from the y direction by the expression in the x direction, the T2's would cancel out, and we would be left with sine theta over cos theta. But we can now apply a trigonometric identity. Sine theta over cos theta equals tan theta. So we end up with tan theta equals negative 0.418, and taking the arctangent of that, we get theta equals negative 22.7 degrees. And since we earlier said that T2 sine theta must equal negative 86.82 j hat newtons, we can work out that the strength of T2 is 225 newtons. In this video, we explored friction and saw more complex examples of force balances. In the next two videos, we will see more applications of Newton's second law.